So in this lesson, we're going to go over the characteristics, the relationships between the sides of special right triangles. The two special right triangle types are those that have two 45-degree angles and one right angle, and then one angle is 30 degrees, 60 degrees, and of course the right angle is 90 degrees. So before you watch the rest of the video or view the PDF, just pause the video right now and just ask yourself, what do you remember about these right triangles, these special right triangles? They're considered special right triangles. The Pythagorean theorem is still going to work, but sometimes if we don't have enough of information to use the Pythagorean theorem, but we know we're dealing with a special right triangle, we can use properties of that triangle to help us find missing sides and then eventually missing angles, because soon enough we will be solving an entire right triangle using some trig values as well as these characteristics. So again, these are the two types of special right triangles we're going to be dealing with. There's going to be a couple ways I write out the facts here. So in a 45, 45, 90 degree triangle, the hypotenuse is radical 2 times as long as the legs. So when we're looking at a 45, 45, 90, both angles are going to have the same measure, which really means it's an isosceles triangle. Then both legs are going to be equal. So I'm going to call each leg just x. That means to get the hypotenuse, that's going to equal one of the legs, x, times radical 2. So again, I'm going to write this out as the hypotenuse is equal to radical 2 just times one of the measurements of a leg, not both legs, just one. Now, sometimes a hypotenuse is missing. That's going to be the easier part, but sometimes we're going to be given our hypotenuse and then we have to find the leg. So to write this out, solving for the leg, all we'd have to do is take the hypotenuse and divide by radical 2. So going back to all of our practice with radicals, rationalizing a denominator is going to come back into play here because we don't want to leave a radical in our denominator. So these are the two sort of formulas to follow to help us find, depending on what's given and what's missing. So on the next page, I have a paper scanned in, but to the best of your ability, just resketch the triangle, or I'll also have this as a PDF, and if you choose to, print out the page with the examples. So let's take a look at some of these again. The first set of examples are all going to deal with the 45, 45, 90 triangle. All right, so as I mentioned, please go ahead and make a quick sketch of each of the triangles below, and then we're going to find the exact lengths of everything else that's missing. So in most cases, there could just be one part missing, or there could be two parts missing. So notice in example A, we have both legs here are 7, so we could have also really had the markings here to show that they're congruent. Technically, yes, you saw some of these examples in the Pythagorean theorem worksheet that, yes, we could use the Pythagorean theorem to solve this, but why not use, it could be a lot quicker, just to use the properties of the 45, 45, 90 triangle. So even though the angles aren't marked here, the fact that the two legs are congruent tells us that this has to be a 45, 45, 90 triangle. So all we'd have to say here is that the hypotenuse, which is A, is just one of the legs, which is 7 times radical 2, and that's it. A is equal to 7 radical 2. I just want to show you, if we were to use a Pythagorean theorem, how we would come up with the same answer. So here we would say 7 squared plus 7 squared equals a squared. So this is 49 plus 49 is going to equal a squared. This will give us 98. And then radical 98, we could say is just, notice how we had to add 49 times 2, so that's going to be, or 49 twice, that's going to be 49 times 2, which turns back out to 7 radical 2. But knowing that fact, we were able to go right to the answer immediately. All right, looking at B, a lot like A, we have both legs are 12, so again, this makes this a 45, 45, 90 triangle, and we could simply say that B is equal to one of the legs, which is 12, times radical 2, and we're right there at the answer. Now for C, this is done a little backwards. E, the hypotenuse, is given to us at 12 radical 2. So we're going to say the leg is equal to the hypotenuse divided by radical 2. So in this case, that's going to be 12 radical 2 divided by radical 2. The radical 2's are going to divide out, so this is just telling us that the leg is just 12 units long. Or if you notice, going back to A, this was 7 radical 2, and then look at the leg is 7. B this was 12 radical 2. Then if you go back to look at the leg, it's just 12. So when the hypotenuse has the radical 2 with it, to go back to the leg, we simply take away the radical 2 because we're dividing by it. So here in this case, each leg, D, is going to be 12, and C is also 12. So it turned out to be the exact same triangle as example B. All right, now for D, we're given a leg here of F. F is 6 radical 2. If I could get this to stay down here. All right, so F is 6 radical 2. I'm going to write this in. And because notice here, there's no marking, so notice that the angle measure was given to us. So this does make it a 45, 45, 90, telling us our two legs are congruent. So G is also 6 radical 2. So H, being the hypotenuse, is one of the legs, 6 radical 2, times the other radical 2. Just because it had the radical 2 there didn't mean that that was already times it. We had to multiply it by another radical 2. So in doing that, remember, when we multiply a radical by itself, we're just going to get the 2. So 6 times 2 is going to give us 12. So in this case, when the radicals were with the legs, we don't have a radical with our hypotenuse. So here H is just equal to 12. And E, again, we're given the angle markings here, or measurements, that they're 45 degrees. The hypotenuse is 10. So just to find one leg, we're going to take that 10 and divide it by radical 2. But now we need to rationalize. So next, I need to multiply top and bottom by radical 2. So this will now become 10 radical 2 over 2. I can divide the 10 by the 2 in the denominator and get 5 radical 2. So this means that I, which is equal to J, they're both 5 radical 2. And you could check. If you were to take 5 radical 2, one of the legs, multiply it by radical 2, you would get 5 times 2, which is the 10 that's right here. All right, so those are the two cases where sometimes the sides have the radical 2 with it, or sometimes the hypotenuse will have the radical 2 with it. Now let's take a look at a 30, 60, 90 triangle. Now, the radical 2 stays with the 45, 45, 90 degree triangle. When we're looking at a 30, 60, 90, we're now dealing with a radical 3. So here, the two legs are going to be different. And how we figure this out, the larger angle will always have the longest side opposite it. So obviously the hypotenuse is across from the largest of the three angles, 90 degrees. So then the second largest side, or the medium length side, is going to be across from the 60. So this is where 60 degrees would go, and then 30 degrees would go up here because that's across from the shortest side. So as we look at this, I'm just going to call the shortest side X. The longer leg is going to be X times radical 3. So notice we have a radical 2 with the 45, 45, 90. And a nice way to remember that is in that 45, 45, 90, two sides are the same. The two legs are the same. So think of the 2, the radical 2 ties in with that. Here we have 3 different lengths of sides. No two sides are ever going to be equal. So we have a radical 3 for maybe remembering it as just 3 different sides. So the short leg is X. The longer leg is X radical 3. And the hypotenuse here is going to be twice the short leg. So to write this out, the long leg is the short leg times radical 3. The hypotenuse is equal to the short leg times 2. Now to go backwards, the short leg is going to equal the long leg divided by radical 3, or in terms of the hypotenuse, the short leg is going to equal the hypotenuse divided by 2. So if the hypotenuse is twice as long as the shorter leg is going to be half the hypotenuse. And then this is where we sort of get this from. If I were to look at an equilateral triangle, see if I could draw this as best as possible. All right, so let's say this is an equilateral triangle. You're going to need this for some of your images. So this is 60 degrees, this is 60 degrees, and notice it's not a right triangle, but I could create a right triangle from this. Imagine that was straight. So here's my right triangle. So what this did was it cut the upper 60-degree angle in half. So this is what's making this angle 30. So if I were to call this length, let's say it was 20, and then it was 20 from here to here, now it's only 10 from here to here. So if this were x, this would now become 2x. And then if I were to go through the Pythagorean theorem, I would find this out. But this height right here, which is the longer leg, this is x radical 3. And just a quick example of this. So if I were to take the 10, I'd have 10 squared. I'm going to call this missing side here, I'll just call it b for right now. So plus b squared is going to equal 20 squared. So I'm going to get 100 plus b squared equals 400. So b squared is going to equal 300. And then I go to take the square root of it. So b is going to equal the square root of 300, which is nothing more than 100 times 3. And then check this out. It's 10 radical 3. That's my short leg times radical 3. So this side right here is 10 radical 3. Pretty neat how that works out. So sometimes you could still use the Pythagorean theorem, but again, it might be a little more obvious with the triangle that we just worked on, the 45, 45, 90, but now we also want to apply it to the 30, 60, 90. So let's go through some more examples here. All right, so go ahead and pause the video and make a sketch for each one as we continue here. But notice again, sometimes both angles will be given, if not maybe just one of them. Again, we're going to find the exact lengths of all the missing sides. So here, the short leg is 7 in example A. Right away, the hypotenuse is going to be double that. So B, real quick, we could say is 14. And then side A, which is the longer leg, that's just 7 radical 3. So it's a very straightforward process when the short leg is given to us. We have to do a little bit more work when the short leg is missing, like in example B. So notice again we have 60 degrees here. Obviously this would give us 30 degrees, which we don't need to write. And it's kind of like the example I just made up. The hypotenuse is given, so that means the short leg, always go from that. We always want to kind of relate it back to the short leg first. We never want to go from the hypotenuse to the long leg or vice versa. Always take it back to the short leg, and these problems will become a lot easier. So that means C is going to be half of 20, so that's 10. And then our long leg is going to be 10 radical 3. So very easy to write in once we understand the relationships between the sides. All right, looking at example C, we have G, which is the longer leg. That's 11 radical 3. So to get to the short leg, I'm just going to abbreviate here, the short leg S, which is F here, really. So that's going to be 11 radical 3, the long leg divided by radical 3, which would just make it 11. That makes sense. To go from the short leg to the long leg, we just take that 11 and multiply it by radical 3. Now to get the hypotenuse, that's just double. So E is our hypotenuse. That's just 2 times the short leg. So this is going to give us 22 here. All right, now for D, that is a 9. That's down there. We have a 30, 60, 90. Here the long leg is given to us. So the short leg, which is J, that's going to be the long leg divided by radical 3. Well, notice in this case we don't have a radical 3 already up here. So like the last set of problems, we want to rationalize, multiply top and bottom by radical 3. So this will give us a 9 radical 3 over 3. The 9 divides by 3 here, so we get a 3 radical 3. So J is equal to 3 radical 3. H, the hypotenuse, is equal to 2 times the short leg. So 2 times 3 radical 3 will give us 6 radical 3. Now keep in mind, you can always check this. Once you have all 3 values, just go through the Pythagorean theorem. I'll show that check real quick off to the side. So we could say 9 squared plus 3 radical 3 squared should equal 6 radical 3 squared. So we're going to get 81. 3 radical 3 squared becomes 9 times 3, so we get 27. 6 radical 3 squared becomes 36 times 3, which is really 108. And then that's what we get here. 108 is equal to 108. So we're good with this problem. So I just want to show you the ratios. Remember how we were working with some ACT problems, and then in the Pythagorean theorem, we were working with some ratio problems. So with a 45, 45, 90, the ratios of the sides is going to be x for the leg, and then it would be an x radical 2. So that's how we could write this out. For a 30, 60, 90. And again, we always want to go in order from smallest to largest. So in a 45, 45, 90 triangle, each leg is going to be smaller than the hypotenuse. Remember, the hypotenuse is the longest side of any right triangle. In a 30, 60, 90, we start off with the short leg as x, and then it's x radical 3, and then it's going to be a 2x. So this is a summary, the ratio of the sides here. All right, so just a nice little review lesson you guys would have seen back in geometry. I know that was a while ago, which is why we're reviewing this. So I will have this posted as a separate PDF, but please work on Special Right Triangles worksheet. There's 16 problems altogether. For the last 4, you are going to have to make a sketch and kind of determine what type of special right triangle you're going to be dealing with. Just like with the Pythagorean theorem, I want you guys to send me pictures of your work in Google Classroom, so I'll have that as a separate assignment post. So you'll have today and tomorrow to work on that to get that into me. So your next lesson will be on Wednesday, where we talk about trig ratios. As always, guys, take care. Let me know if you have any questions.